Alright, today I'm going through the book's Structure and Interpretation of Computer Programs. I made it to the chapter on procedures, and we're gonna start on the topic of procedures as general methods. I have a new wallpaper. I think I need to stop with the snowy wallpapers as the weather is getting better and better. But yeah, it's a new one. And hopefully I will have a new one every video, let's see. So, let me open my tablet. Procedures as general methods. Okay. So, I was following the book, and the way the book is written might feel a bit esoteric, so to say, but I think it's just trying to reiterate the same thing I've learned as a junior developer, and all the concepts basically that you learn as you start programming. Basically, we have written procedures, and then we have written higher order procedures, and then we actually understood how abstraction actually works. We have procedures that are expressing wider methods of computation, which are independent of the particular things that we want to write, that we are involved into, basically. So, there is something called the half interval method, which is a simple but powerful technique for finding roots of an equation f of x equals 0. Half interval method. What does it do? Finds roots of an equation f of x equals 0. F of x 0. Alright. What is f? F is a function. Actually, f is a continuous function. The idea is that if we have points a and b, such as f of a is less than 0, which is less than f of b, f must have at least one 0 between a and b. How can we locate a 0? To locate 0, alright, to locate a 0, x, let x be the average of a and b. To locate a 0, we're going to make x the average of a and b, and then we are going to compute f of x. To locate a 0, set x to be average of a and b, and then compute f of x. All right, f of x. If f of x is greater than 0, then f must have a 0 between a and x. If f of x is less than 0, then f must have a 0 between x and b. And we can continue in this way. And we are identifying intervals on which f must have a 0. When we reach a point where the interval is small enough, we can stop the process. So what are we noticing here? We are actually reducing the area of uncertainty by half at every step of the process. So the number of steps is actually theta of log of L over T. What's L? L is the length of the original interval, and T is the error tolerance. Alright, we can write an actual procedure that implements this strategy. Alright, let me show you the method. But first of all, let's talk about, what's a root? So a root of a function is simply a number where the function equals 0. If I had f of x is equal x minus 3, f of 3 is 0. The root is x equal 3 because f of 3 is 0. It's basically where the curve crosses And what the half interval method really does, it just guesses. It does it in a smart way though, but it guesses without specific guarantee. Basically, if we have a continuous, maybe not something like this, a continuous function, and if at a certain point the function is negative and another point the function is positive, so somewhere between these two values the function must cross zero. It cannot jump, you know, from being positive at this point to negative at this point without crossing zero. And that's it. That's the entire guarantee basically. And a simple example could be if I had a function that says x squared minus 2, and I want to find the root of it basically, we can do f of 1 is equal to 1 minus 2 minus 1. F of 2 is equal to 4 minus 2, 2. So we have a negative and a positive value here. So we know that between these two values of 1 and 2, the function crosses 0. And so what do we do next? We look in the middle. We find the middle value, just the middle value, which is 1 plus 2 over 2. I think we did something similar in one of the last exercises. 1.5. We plug in 1.5, it's 2.25 minus 2 is 0.25. So you see what's happening now? This is a positive value. So we know that f of 1 is negative, f of 2 is positive, but f of 1.5 is also positive and it's less than f of 2. So we know that the root must be between 1 and 1.5. And we cut the interval in half, and we just continue and we repeat. We are checking the sign, we are keeping the half that contains the sign change. We are basically zooming in. So we could divide it as many times as we could do, you know. I could zoom it, I could keep dividing it. So we need to have a way. Just do all of this. We need to have a way, you know, because eventually the interval becomes very small. We need to say, okay, good enough. That midpoint is our answer. And then we just create a method close enough that does this. If the interval is small, then I don't know, any threshold that we deduct. So let's decode. Can I put maybe like a dark here? By singular code. We are defining our search method definition right here. We have a function, negative point, positive point. We are looking for the midpoint, of course. If okay, they are computing the average of the negative point and the positive point here, and we are computing the middle. If it's close enough, basically if it's small enough, we are returning the midpoint. Otherwise, we are testing the midpoint again with the test value, and then we are deciding which half to keep. We have a condition. If it's positive with the test value, I think it needs to be presented. If midpoint value is positive, we know that the root is then, and we are calling the search method again, the root is then between the negative point and the midpoint, because we halved basically the problem in half. Then we are testing the value for negatives. If it is negative, I think I also need to indent this one as well. If it is negative, root is between midpoint and positive point, otherwise we return the midpoint. And this is basically just the bisection method because we cut in half every step. I also mentioned that it takes this amount of steps here. And that's it. So this one run, I think, good. Here we have some issues. All right, so we also need a function for close enough. I think this one will be all right. And now if I run it, average. I also need this identifier right here. Right, so average is missing, it's not built in. We need some helpers. So we need some helpers. This is not one. This is the average method here. Program did not output anything. All right. All right. So we have a code here that's working close enough. Copy all of this. Okay, if I run it, nice. So basically, what I did here, these are the helpers. Average, close enough. This is our bisection half interval search method. And here's our example as well. So basically what we are doing, and let me just go back here. We are taking this as an example, the same one that we just did. All right, so as we said, we picked the endpoints with opposite signs. Why have I deleted it first time? 1 squared minus 2 is minus 1. It's negative. F of 2 is 2. This is positive. We take the midpoint. And so on and so on and so on. All right. Usually how I like to go through this is to do some exercises. I would skip or skim most of the theoretical part and just hit some questions. I think it's the best way actually to learn, in my opinion. So let me just find it. All right, I have one exercise right here. So the problem says, this is the exercise 135. Okay, close this. I just pasted these two examples here. Let's do this example. Show that the golden ratio B is a fixed point of this transformation, and use this fact to compute phi by means of the fixed point procedure. Okay, the golden ratio is a special number that shows up in math, geometry, art, I don't know, nature. The approximate value of it is 1.618 something 0. Here it says 339. Okay. And one common definition is that phi is the positive solution of phi is equal to 1 plus 1 over phi, which is basically the whole exercise. And if I do it in the calculator, I have this number right here. Let me just move the calculator here. If I put in 1 plus 1 divided by this value, I got this value. I haven't copied the whole value itself. What if I copy the rest of it? Will I? Let me type 339,887 1.339. I mean, it is close enough. So what is a transformation here? A transformation is just a fancy word for a function, basically. Transformation right here is a fancy word for a function. It takes a number and outputs a new number. And this is the transformation. X goes to 1 plus 1 over x. Take x, compute 1 plus 1 over x. So if we have x equals to 2, I would have 1 plus 1 over 2. This is 0.5. This is 1.5. If x is 1.5, I would have 1 plus 1 over 1.5 plus this 0.6. So it's 1 plus 0.6. It's an infinite number, 1.666. The arrow here means, this arrow right here means that x is being sent to this function right here. It's literally the definition of a function. What else might be? Fixed point. Maybe that's another keyword that's interesting. A fixed point of a function is a number that doesn't change when we apply the function. Formally, this could be written by saying x is a fixed point of a function f if f of x equals x. An example of this would be if f of x is equal to x squared. What is the fixed point here? It's either 0 or 1 because they only satisfy this formal definition for this function right here. So show that the golden ratio p is a fixed point, all right, of this transformation. So we already have this kind of explained to us, and we use this fact to produce it. And what else? The fixed point procedure is actually the thing that we are also find interesting. How can we solve this exercise? The gist of it is that we need to show that phi is a fixed point of this function right here. And if we have a transformation, f of x is 1 plus 1 over x, we need to show that f of phi is equal to phi. So in order to compute f of phi, we are doing this. But we already have seen and we have calculated that the golden ratio satisfies this equation right here. So basically we have proven this right just now. But we can also prove it using the fixed point function. So let me go back to the code. I'm gonna remove all of this right here. I think this is the fixed point. Right. So it should output something that's really, really close. So what is happening here? All right, we have the tolerance. We have the fixed point method, our function as well. And our function here is defined here. So we are calling phi, and phi is calling the fixed point procedure here. With this, do you remember what lambdas are? With this instantaneous method, which takes the number, adds it to the division of 1 over x, and our first guess is 1. So we have our function, and we are starting at 1, and then we what's this? Okay, this is the definition of the close enough method, so we can skip this. We can skip this as well. And this is where we are continuing. I'm trying this method with the first guess, which is 1. If our first guess is 1, we are moving the execution of our procedure here. The next is set to the function with the value of guess. So we are providing 1 here. Blah, 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 blah. If close enough, it's not close enough. We are just going next. So the next value would be 2, I think. All right, so we hit it again. We are trying the next value. The next value is 2. We put 2 here. We do the same thing. 2 will give us 1.5. We check if it's close enough up to this threshold. It's not close enough. We do it all again. The next value would be 1.666. And then we would reduce this error value up to a point at which we get this output. And we can say safely, all right, it's gonna wiggle around and settle around 1.618033. And this settling point is the fixed point. This is the golden ratio, basically. Let's do another one. Exercise 1.36. Modify fixed point, which was this method, so that it prints the sequence of approximations. So basically, when we are trying to solve an equation, but we can get the exact answer immediately, we are starting with a guess, as we just did, as we just showed. And we are repeatedly proving it. And basically, these guesses that we generate are the sequence of approximations, which, you know, each number is closer to the real answer. Using the new line and display primitives shown in another exercise, right? Then find a solution to x over 2x on x equals 1000 by finding a fixed point of the logarithm of 1000 over logarithm of x. Use scheme's primitive log procedure, which computes natural logarithms. Compare the number of steps this takes with and without average damping. Note that you cannot start fixed point with a guess of 1, as this would cause division by log 1, which is 0. Okay, logarithms are simple enough. Basically, they are just asking what power do I need. The logarithm b to a means, all right, what power must I raise b in order to get a? For example, if I have logarithm of base 10 of 1000 is equals to 3, because 10 to the power of 3 or 2000. So this flavor of scheme that we are using, the log function is the natural log. So log x means ln of x, and the base here is e, which is approximately 2 point. So what are we gonna use? We are gonna use log b of a, and this will be ln of a over ln of b. So what we will have is here log of x, base x of 1000, and if we follow the same steps that we have here, down here we'll have log x, sorry, not log of x, ln of x, ln of x, and above we will have ln of 1000. And what else is interesting? Average damping. Average damping is a trick to reduce while jumping, so the gases are converging instead of oscillating. If we update our function to f of x, average damping will replace it to another function. So instead of going straight to fx, we go halfway. So what do we want to see here? We want x to the power of x 2000. So we want to take the natural log of both sides. X to the power of x, the natural log of 1000. So we have a rule, an algorithmic rule that does this: ln of x ln 1000, and then we are solving for x. I have ln 1000 over ln of x. So basically we have fixed point form where where x is equal to f of x, and f of x is this function right here. First things first, let's go back to the code here. We need to modify fixed point to print approximations. First line, okay, close enough, okay. Try guess. I think here, then print a new line. That display step. We also need to add a step here. Try guess step. Display this. Display guess. Guess close enough. Guess next. Next. Try next, but here we also need to add the step as well. And we should increase the step by 1. Drive, let's get 1. Will this work? Hopefully it will. And you can also solve this without damping. I can remove all of this. Let's try it. I won't start it there. 1. Wait. I won't start it at what? Alright. And if I run this, is this correct? I don't think. So this solves it without average damping. But with average damping, we are just adding an averaging function. And let's solve it again. So basically, without damping, the values usually bounce around and converge more slowly. All of this. With damping, we have the sequence which is stabilizing in a lot fewer steps, basically. So average damping aids convergence. Okay. All right. Let's stop here and see you in the next video. Bye.